welcome to another module in this massive open online course. So, we are looking at example problems in the analysis of continuous time and discrete time LTI systems, right, linear time invariant systems. Let us continue looking at these examples. Okay. So, we are looking at example problems for the analysis of LTI systems. Okay. And let us start looking at another problem, which is basically we are given that x t equals u t minus u t minus 1, where u t, remember, this is the unit step function. U t is the unit step function. We want to find out what is y t equal to x t convolved with x t. What is this? First, let us try plotting u t x t. Now, we know u t is the unit step function. Okay. This is given by 1, t is greater than or equal to 0 and 0 otherwise. This is the unit step function, which is equal to 1 if t is greater than or equal to 0 and 0 otherwise. Now, u t minus 1 is the unit step function delayed by 1. So, this will be, take the unit step function and delay it by 1 unit. So, this is unit step delayed by unit step delayed by 1, and therefore, x t you can see, which is equal to u t minus 1, this will be given as this will be given by the function which is equal to 1 when 0 less than or equal to t less than 1. So, this is x t, which is u t minus 1 equals 1 if 0 less than or equal to t less than 1, and this is 0 otherwise. Okay. So, this is your x t. Basically, it is a pulse of height 1 between 0 and 1. You can clearly see this is a pulse of height equal to 1 between 0 comma 1, that is from t equal to 0 to 1. Okay. And now, we want to convolve x t with itself, convolve x t with another x t, which is again obviously this is going to be a pulse of height 1 between 0 and between 0 and 1. Okay. Now, to convolve, remember, we need to flip first. We are convolving x t with x t. So, we need to first flip it about 0. So, let us say this, we make it as the tau axis rather than the t axis. So, we make this as x of tau and this is becomes your x of tau. So, x of minus tau will be flip about the y axis. So, this will be pulse of height 1, this will be pulse of height 1, and between -1 and 0. So, this is your x of minus tau, and x of t minus tau will be delayed version of this by t. So, x of t minus tau will be shifted to the right by t as we have. So, this is t, this is t minus 1, and this is x of t minus tau. Okay. So, this is your tau axis, this is x of t minus tau. Okay. And now multiply this with x of tau. Remember, x of tau is still a pulse of height 1 between 0 and 1. Okay. So, this is a pulse of height 1 between 0 and 1, and so this is your x of tau. So, multiply x of t minus tau by x of tau, integrate from 0 to infinity. So, this is basically the area of overlap between these two pulses, which can be seen to be. So, you can see integral minus infinity to infinity x of tau, x of t minus tau d tau. Remember, for x of t minus tau, we flip about the y axis, that is, look at x of minus tau and then delay it by t, shift it to the right by t. Okay. And now you can see the overlap, corresponding overlap is of t height 1. So, this will be equal to 1 into t equals t. Okay. And therefore, this increases linearly with t, increases linearly with t for 0 less than equal to t less than 1. Now, once t greater than 1, from for t greater than 1, it decreases again. You can see, right, for t greater than 1, you can see it again decreases linearly, greater than 1 or greater than equal to 1, decreases linearly because overlap progressively decreases until it reaches 0. So, which means this will look something like, from 0 to 1 it increases. So, this is at 1, from 1 it decreases until it hits 2. So, this is t, this height corresponds to the maximum overlap, which is 1, and this is therefore, this portion will be 2 minus t. Okay. So, this is your y t equals x t convolved with x t, and you can see this can be described as 1 minus mod magnitude t minus 1 for 0 less than equal to t less than 2, and this is 0 and this is 0 otherwise. Okay. So, this is basically your triangular waveform. Or not a waveform, a triangular pulse basically. So, the convolution of two square pulses of equal width, correct, the convolution of two square pulses of equal width and height, that is convolution of square pulse with itself, yields the triangular pulse. Okay. This is 1 minus modulus of mod of t minus 1 for 0 less than equal to t less than equal to 2, and this is 0 otherwise. Okay. So, this is basically the result of the convolution. Let me just write it over here once again. This is 1 minus magnitude t minus 1, 0 less than equal to t less than 2, and this is 0 otherwise. Okay. So, this is the solution. This is the final solution. Okay. Let us now look at the next problem, which is that of a periodic convolution between two periodic signals. Periodic convolution is defined thus: let x1, x2 be periodic with a common period t naught, let x1 t, x2 be two signals which are periodic with common period t naught, capital T naught. The periodic convolution f of t is defined as 0 to t naught x1 tau, that is convolution over one period, x1 tau x2 t minus tau d tau, and it is represented as x1 t with this kind of a symbol. Okay, and this is termed as a periodic convolution. And it is desired to show that this periodic convolution remains unchanged if you shift it by small t naught. So, show that f of t if you shift the integral by small t naught, that is x1 t x2, that is if you denote this by f tilde t x2 t minus tau d tau, we need to show that this is equal to f t, that is you are shifting the integral by t naught. Shifting integral by small t naught, any arbitrary value small t naught. Okay. Now, the solution can proceed as follows. First, observe that now let us set phi of t, now let phi of tau for any given value of t equals x1 of tau x2 of t minus tau, that is phi of tau for, or let us subscript this by t to show the dependence also on t for given t. Now, we will show that phi of t of tau. Now, let us look at this phi of t of tau plus t equals x1 of tau plus t naught into x2 of t minus tau plus t naught, which is equal to x1 of tau plus t naught into x2 of t minus tau minus t naught. Now, look at this x1 of tau plus t naught, that is shifting by period, this is equal to x1 tau times x2 of t minus tau minus t naught is also equal, is again equal to x2 of t minus tau, which means this is equal to phi t of tau. So, what we have shown is phi t of t plus tau, phi t of t plus t naught is equal to phi t of tau. Okay. So, we have shown that phi sub t of phi sub t of tau plus t naught, phi sub t of tau plus t naught equals phi sub t of tau, which means phi sub t of tau is periodic, okay, which means this implies phi sub t of tau this is periodic, which implies that basically integral over any period is same. So, you have integral 0 to t naught phi sub t of tau dt is integral, you can shift it by any constant quantity small t naught. So, integral this is equal to phi sub t of tau dt, which is equal to t naught plus tau naught to small t naught plus capital T naught x of tau x2 of t minus tau d tau, which is equal to f tilde of t, and this is f t. Okay. And this follows because for a periodic function integral over any period is the same. That is, if I have a periodic function with period t naught, if I consider any duration, right, any time interval of duration capital T naught, then the integral will be same. Therefore, integral 0 to capital T naught will be the same as integral any small t naught to small t naught plus capital T naught. So, integral over any interval of duration capital T naught, where T naught is the capital T naught is the period, will be the same for a periodic function. Okay. So, we are using that property. Okay. So, basically shows that, which shows that the periodic convolution also remains unchanged when you consider any time interval of duration capital T naught. That is the basic idea behind this periodic convolution, which is defined for the convolution of two periodic functions with a common period capital T. Okay. Let us look at the next example, okay, which is consider the system with the impulse response h of t equals e to the power of minus t square by 2 minus infinity less than t less than infinity. So, we want to ask the question, is this Bibo stable? Is this system Bibo stable? And the solution can proceed as follows. For Bibo stability, remember the condition for Bibo stability we have to have minus infinity to infinity must be finite, that is the impulse response must be absolutely integrable, that is integral minus infinity to infinity magnitude h t dt should be a finite quantity. Okay. So, this quantity should be finite. Now, if you look at e to the power of minus t square by 2, you will realize that it is given basically by a Gaussian pulse, which is, this is a standard signal, this is known as the Gaussian pulse. E to the power of minus t, it has a bell shaped, also known as a bell shaped function. This is also known as a bell shaped, looks like a bell, therefore also known as a bell shaped function. Now, this is always positive, e to the power of minus t square by 2. So, therefore, integral minus infinity to infinity to check Bibo stability, integral minus infinity to infinity equals integral minus infinity to infinity magnitude, but this is always positive. So, this is simply h of t. Now, this is also e to the power of minus t square by 2 is also, you can see. Now, what I am going to do is I am going to multiply by square root of 2 pi, and this is integral minus to infinity 1 over square root of 2 pi, this is 1 over square root of 2 pi e to the power of minus t square by 2. Now, you can show that this integral is equal to 1, because this integral is minus infinity to infinity of a Gaussian probability density function. So, 1 over square root of 2 pi e to the power of minus t square by 2, this you can show is a, Gaussian probability density function, that is 1 over square root of 2 pi sigma square e power minus t square by 2 sigma square is a Gaussian probability density function with mean mu and variance equal to sigma square, and integral minus infinity to infinity Gaussian probability density function is 1. Here you can see the variance is sigma square is equal to, here you can see the variance is sigma square equal to 1. If you simply substitute sigma square equal to 1, all right, you get the Gaussian probability density function with sigma square equal to 1 and mean is 0. So, that gives the Gaussian probability density function 1 over square root of 2 pi e raised to minus t square by 2, all right. So, that is the Gaussian probability density function for the range t lying between minus infinity to infinity. So, this integral is 1, implies the net integral is square root of 2 pi, which is a finite quantity. So, this is a finite quantity, hence the system is implies a system is indeed the system with impulse response given by the Gaussian pulse is indeed Bibo stable, okay, because it is the integral absolute integral, that is it is absolutely integrable, that is integral minus infinity to infinity magnitude h of t dt is a finite quantity. Okay. All right. Let us now proceed to the next example, which is given by the, consider the LTI system given by consider the LTI system where the output y of t equals minus infinity to infinity e power minus j omega naught t minus tau x of tau d tau, this is the output. So, for input x of t, this output y of t is given by this relation. What we need to do is we need to find the impulse response and also eigenvalue for the function eigenvalue for the function e to the power of st ut. Okay. Or let us put it this way, this is, let us make it e to the power of minus t minus e to the power of minus t minus tau times, or let us keep it this way, e to the power of minus j omega naught t minus tau x tau d tau, and find the eigenvalue corresponding to eigenvalue for function e to the power of st ut. Now, it is easy to see what the impulse response is. The impulse response of this is equals, well, you can write this as this is integral minus infinity to infinity minus j omega t minus tau x tau d tau. So, this is your h of t minus tau and this is your x of tau. So, this is basically h t convolved with x t implies that the impulse response is e power minus j omega naught t. So, the impulse response of this system is e power minus j omega naught t. Okay. So, all right. So, we will stop this module here. We are looking at some examples of the analysis of LTI systems. So, we will stop this module here and continue with other similar examples in the subsequent modules. Thank you very much.